Wonderful. Well, yeah, welcome in everybody. We are here to walk you through some XAI or explainable AI methods. We figured we wanted to use this time to introduce just a couple of methods and then get hands-on with a toy problem. Well, a semi-toy problem. It's real data, but it's a rather easy explainable AI method or data set. And then we wanted to give you a chance to talk about your work and ask us questions. So we're hoping that the actual presentation and tutorial part takes about 35 minutes. And then with the rest of it, we can start discussing with you how you think you want to be implementing this stuff. And with that, yeah, I guess we'll get going. So again, we work at the National Center for Atmospheric Research. We implement a lot of machine learning within our workflows and within our science, and we found that some of these explainable AI methods have been really powerful to sort of peering within the black box to see exactly what these networks are saying or looking at. So for today, we're going to be looking at a network that classifies the El Nino Southern Oscillation. So for this, we're going to use a sea surface temperature data set. So it's the extended reconstructed SST version 5 from NOAA. And we're going to be studying the years 1950 to 2021, and we'll be using monthly resolution. So that's about 851 data points here, or snapshots of SSTs spanning these months. And just in case anyone is not familiar with what El Nino is, I'm showing a GIF of, this is a maximum covariance analysis between the Nino 3.4 region that you see in color fill, or it's expanded beyond that region, but we do the MCA across this Nino 3.4 region, which is sort of the middle of the tropics there, and the surface pressure, which I'm showing in contour. And that's as it moves across an El Nino year. So it moves from, I think, early November down into and fades through November. And you see sort of this seasonal development of this pressure pattern that we call the Pacific North American pattern that affects downstream weather. And this is really why we care a lot about the El Nino Southern Oscillation, is that on seasonal timescales or even subseasonal timescales, these sea surface temperature patterns can, I see a question. Oh, he's introducing himself. Wonderful.
Hello.
Welcome. These sea surface temperature patterns can have a Rossby wave or downstream effect that then influences surface pressure or surface temperature and precipitation across the US. And interestingly, we're walking into what we're projected to be a big El Nino year. If you look at the Columbia IRI hosts a big suite of model ensembles, and some of them are projecting over 2 degrees sea surface temperature anomaly. So again, we're looking at these SST patterns, and we're showing an anomaly pattern here. So really what the El Nino Southern Oscillation is this Central Pacific warm or cool sea surface temperatures that then have global implications for different weather patterns. So today we're going to be building a neural network that is tasked at identifying whether this sea surface temperature pattern is characteristic of an El Nino or a La Nina. So it's a really, really easy task for this network to do. But then we want to take these methods that we're going to be talking about, turn the network around, and see what the network has learned about the characteristic traits of an El Nino Southern Oscillation. So to do that, this is the network we're going to be devising. So we're really just taking the SSTs at each grid point, and we're going to flatten those out and make a feed-forward neural network. There's no convolution. It's pretty much as simple as you can go. So we take those points. We exclude the land points for obvious reasons. And we flatten those out, push it through a couple of hidden layers with ReLU activation, I think, so rectified linear unit activations. And then the output layer will be just 2 nodes, and it will be either this pattern is an El Nino or this pattern is a La Nina, and it will predict the probability of that. So we're going to use categorical cross entropy to predict the probability of either a La Nina state or an El Nino state. And again, we want to turn this around and say, what did it learn about the sea surface temperatures that characteristically puts it in one of these 2 regimes?
Okay, this is just an acute schematic form of that question that we just asked, which is, how did the network come to its conclusion? And you can see all of us looking very confused about what is happening inside that neural network. And then we can use explainable AI or XAI or explainable artificial intelligence to take what the neural network outputs as its prediction and, quote, back-propagate it through the neural network, back-propagate this information through the neural network to identify specific regions in our original input image that the neural network used to actually make its prediction. That's one really big motivation behind explainable AI, is we can actually understand and look into the black box. So understand how the neural network makes its prediction. For example, for a lot of geoscience or earth system science people, they want to know, is this actually physical, or is it identifying some random spurious thing like the land or something that we know isn't actually useful. We can also use it to fine-tune and optimize our neural network. So let's say our neural network isn't performing very well and we want to know, like, what is it looking at? And maybe it's looking at some region near Antarctica. And we're like, well, we're trying to predict El Nino or La Nina, so that's not very helpful. And maybe we want to just shrink the area of which the map we're giving to the neural network. So instead of giving it a full global SST map, we give it just tropical SSTs. And we can start fine-tuning and optimizing either the input or actually how our neural network is set up. And then, is there something new that the neural network has learned that we may have seen before but never thought of as connected to our specific problem? So there are a decent amount of XAI methods, and we're going to talk about just two today, these first top two: input times gradient and optimal input, also known as backwards optimization. There's also layer-wise relevance propagation, integrated gradients, and feature importance. These are all attribution methods, meaning that the XAI method tries to assign a contribution to a specific pixel within your input that led to that specific output. And I highly recommend this paper that is incredibly small on the screen by Antonius Mamalakis. And he has a synthetic data set that he's created, and he goes through actually each one of these different XAI methods and shows how well they perform while you actually know the answer to the problem. And like I mentioned, today we're talking about the first two, and then while we're chatting about how we can apply these or others to your specific problem, we're also happy to chat about other methods that you can use. So just to start on input times gradient, we'll go into the actual methodology behind this, but it's actually one of the more simple methods. The goal is to identify regions, like we had been talking about in the input, that are relevant for the output. And in simple language, we're trying to answer the question with this methodology: where does the network look in its input image to make its prediction? And so to do this, just this bottom equation here is the entire thing. So you're going to calculate the partial derivative, which is this df dx, of the network's output with respect to each input pixel. And basically what this does is quantifies the sensitivity of your network to changes in your original input image, or this x. And f is this function that your neural network has learned, or a representation of the function your neural network has learned. And so you can imagine that if your input leads to a large change in the output, then your gradient is going to be large, and that suggests that that point is most likely important for the prediction. And then the method is exactly what the title says. You just multiply the input times the gradient, and that attributes the importance of that specific grid point via the gradient to your specific region that you're looking at. So there are pros and cons to each one of these XAI methods. One of the pros of this one is that it's simple and really fast, and it's a really simple and fast way to identify these regions. And it's actually a conceptual basis for a lot of other XAI techniques. So integrated gradients is another version of this that tries to account for some more nonlinearities in the methodology. And it's basically, instead of multiplying by the gradient, you multiply by the average gradient between some baseline and input. That's very detailed, but you don't need to worry about it. And if you want to know more, I can answer questions later. And then, for example, I mentioned layer-wise relevance propagation, or LRP. When you use that ReLU activation function in your neural network, LRP actually reduces to input times gradient. And so you could just use input times gradient instead of LRP if you just use the ReLU activation function. Some of the cons of this method is that you're multiplying your input times your gradient. So that means even if your gradient may be smaller, if your input is really large, it can assign high relevance to that region, and that may not actually be important for your neural network in the first place. And it's not very useful for larger, more complex problems. It can be affected by gradient shattering or noisy gradients. Yeah.
Cool. So yeah, the second method that we're going to be talking about today is called optimal input or backwards optimization. And really the goal of this is to have your network construct its ideal sample to give the highest predicted probability of a predicted class. So in simple language, I want to ask the networks to show me what it thinks is the easiest sample to classify. The home run, I knocked this out of the park. This is going to be super simple. So the little schematic on the bottom shows basically the process of what this is. We're going to ask the network, what do you think a dog is? First, we train a network that classifies dogs or cats. We say probability of dog is high. Say, what is a dog? And we feed this network just a blank matrix. We say, here is a matrix of equal input space that we want to see back out. We then back tune the network. We basically run the network backward and it says, let me construct my ideal case of what a dog is. And it says, here's a dog. And it gives us a nice picture of a dog. Super fun method. It will reconstruct things that are physically interpretable for scientists like us that know the field well, so you can really lean on your domain knowledge to say, oh, this is really what the network is looking for. It's really fast and simple to implement, and when I first heard about it, I thought it was by far the coolest method ever. I was like, oh man, this solves all the problems. This is great. We can just run this backwards. Fantastic. However, it only provides one optimal input. So what if there are mixed inputs that you're seeing across that space? It's really tough to pick things out from it when your samples are not necessarily clean. So given maybe a central versus an eastern Pacific ENSO, it's hard to tell maybe sometimes what the network is actually constructing. I found it very, very tough to implement when it's a really low signal to noise problem. So when the network is it's low skill, there's a lot going on there, and then you try to reconstruct it backwards. Oftentimes you find that the reconstructions don't make a lot of sense. So really picking the problem well is a good way to start with these optimal input methods. And also, one way to kind of fine-tune your network, and it goes back to what Kirsten was saying, that you can use these methods to actually think about the architecture and the choices you've made, is what if the CNN or ANN is really only training on one pixel or one really small region? And when that lights up, it's just your optimal input would just be, one pixel or one hot or cold thing. Maybe that means you can start to use methods to make sure your network is more generalizable, as in drop out some of these regularization methods that will spread the input across multiple features. So in that case, it really wouldn't tell you something about your input sample space. It wouldn't construct a full physical domain, but it will really just leverage what the network uses. So you can start to make choices within your network to maybe fix that last point a little bit. And here's the illustration of what's actually happening while you're doing a backward optimization process. And this is from Ben Toms et al. That came out in 2020. So the big idea behind this is first you define your problem and you train a network. And I think for any method that we talk about today, this defining the network and being intentional with your network choices and knowing that you're going to be running XAI from the beginning, super important. So don't think about XAI as the last figure in your paper. Start to think about it as, okay, we're going after a question here. How can we start to optimally design a network that goes to answer that question? So in this case, we've designed a network that we know will be skillful and easy to do. So we train this network. We then identify some desired output. So in this case, we'll say, let's optimize for an El Nino. So we put a 1 here as the probability of the output. We then generate an input space, which in this case would be all the points of SST across the globe. And we pass all those 0 inputs into the network and calculate the loss. So in this case, the network output for this example is 0.1% El Nino, 0.9% La Nina. No reason why the network made those choices with all zeros. Sort of just a bad figure for that. Yeah, it should be 0.5, 0.5. Not to critique Ben. But it then calculates this loss. See you later, DJ. It calculates this loss, and then what we do is we backpropagate that loss through the network. So we calculate the gradient of that loss through the network while maximizing one of these output nodes. So we say, we'd like to make this node right here equal to 1, so we calculate the difference there, calculate the gradient, push it back towards the forward. It then reconstructs that gradient space, and then we add that delta to the input. And you iterate that forward and forward until the loss becomes 0, and what you've done is you've added some amount of input to your originally 0 input space, and it says the optimal input is actually this SST that we move forward with. So with that, we're going to move over to the notebooks and show you how this is done. So does everybody have the link to the GitHub? Seeing nods? Seeing nods? Has everybody loaded it up? And the first notebook we're going to open is just called Run First. Named intuitively, I think. Cool. Good? 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 Wonderful. I think we're good to go. Okay, so all this is doing is first we're just installing wget, which just it is a application that lets you pull things from different repositories. We import that package, and what that's going to do is pull from Libby Barnes' GitHub here, and it is the data set of SSTs that we've been talking about, and that pulls that down to your local directory, which is here. So now you can see once you've run this, you should have this netcdf file show up in your Active Directory. So
there's just one. That has 2 because we've downloaded it twice now.
We've done this a couple times.
Yeah.
So everyone should just have one data set here. Cool. And then the next thing we're going to do is actually construct our neural network. So you can move over to Predict Enzo, the Predict Enzo notebook. And the first thing we want to do is credit Libby Barnes here, because she actually constructed this problem, and it's something that we're pulling and then added to. So here again, we're training a classifier to predict whether it's an El Nino or a La Nina event. And the input is a map of global SST. The output is a classification of either Enzo or La Nina or El Nino. And again, we're trying to maximize a probability here, so it's a categorical. So I'm going to run this and then run the load the libraries here, and it will kick you a little error because we are using, for all of this, we're going to be using an older version of TensorFlow, so we're using the TensorFlow 1 implementation. What's that? No, we're using the TensorFlow 2 implementation, aren't we? No, we're using the TensorFlow 2 implementation.
You can just ignore the warning.
Yeah, but the backwards optimization uses the, calls the old toolbox. Anyway, so we'll do some pre-processing. All this is doing is going to take the Nino region, which is this -5 to 5, or 5 south to 5 north, 190 to 240 east, and create this time series of El Nino, which is really just the anomaly of this index. So if you run this cell, you will see this nice figure pop up that says anytime it's above this 0.5 anomaly here, we're going to be classified as an El Nino year. Anytime it's below, it is a La Nina year. And we are going to do a little bit more of data prep. And all this does is classifies events into either El Nino or La Nina events. So if you run that cell, just a little bit of hand holding, and then we are doing grabbing the training indexes, the validation indexes, and the testing indices. And those will be plotted here. So we're going to train on anything pre-1999. So you can see this big 97, 98 El Nino event. We're going to validate on 2000 to 2010, and we'll test on 2010 to 2020. And again, if we standardize the training, here what we've done now is selected that region and prepared all of our training data. So here's the neural network itself. So for this, we'll have a very simple network. It's 2 hidden layers, 12 nodes apiece, super small. We're going to use L2 regularization, and our learning rate is going to be set right here as a small number. We'll run it for 20 epochs with a batch size of 32. And if any of those terms are unfamiliar to you, let's chat after the workshop here. And then our activation will use a rectified linear unit, and our loss, again, is categorical cross entropy. So what this whole node does is builds the model, adds these layers, adds the final layers, and then compiles it using Atom. And we're going to optimize using Atom optimization. It then fits the model, and it'll show how well we actually have optimized it. So you see it's super small, so it trains really, really fast. And if we look at our loss curves for our training versus validation, we can see that we are not overfitting. We are optimally fitting both the training and validation data set. And after about 5 epochs or so, we have a network that is just about 100% accurate on both our testing and our training data. And we can run that on the test data set and show a confusion matrix here that says there are 43 La Nina events. We've categorized all 43 of them correctly. There are 27 true El Nino events. We've categorized all 27 of them, those correctly, and we haven't missed a single one. So we have a really, really good network that knows what the sea surface temperature looks like. So not a hard problem, but neat that you can train a machine to do it. So then if we just look at composites of those 2 fields, this is what the composites of all of the El Nino predictions look like, and the composites of all the La Nina predictions. You can see that this looks very, you have your characteristic warm SSTs for your El Ninos and your cool for your La Ninas. It's got more of a PDO signature and less of a tropical signature, but still, I think that should be fine. And if we're happy with this model, we're going to go ahead and save it in a directory that is within our system. So we have our saved model, and it's going to be called enzo model.h5. And with that, I'll hand it back to Kirsten. And anything that I missed, please clean up.
Okay, great. If you don't have saved model as a directory, you can uncomment that top line and then run that whole thing, and it'll save your model.
Are any errors being kicked up now, or is everything running smooth? Wow. Okay.
Well, that's fantastic.
That's
yeah. Will mentioned that these look a little funny. One, we're looking at the testing data, so it's only 10 years. And then 2, we've trained the neural network to pick up the Nino 3.4 region, which is how we define ENSO, and that's located around here. So you can see that this has our standard warm SST, and then La Nina as well.
We're also
cold.
doing full year, so this isn't just the characteristic.
Yes,
like
that
winter
too.
time. So
Great point.
Some of the NPM will come in there.
Does everyone have a saved model? Good, good,
Cool.
good.
Feeling good?
Good.
All right.
Everyone's loving it,
And do
having
we have
fun?
are there any questions now, just as an intermediate step?
Everyone understood what happened?
Cool.
Great.
Wonderful.
Okay. So now we're going to do input times gradient. And we've made composites of the SST that we've input and what the neural network correctly classified as El Nino and La Nina. But now we want to look at what from those images did the neural network use to actually make its prediction? Did it use the whole basin, the whole tropical basin? Did it use the specific Nino 3.4 region? Did it use a combination of the two? And that's what we're going to do here. The input times gradient code is provided by Antonius Mamalakis from Libby Barnes's group. Okay, so you can go ahead and load these libraries and functions. And then I'm going to stop us on the input times gradient function quick. And this is just a function to get the gradients, nicely named. And basically what's happening here is we're calculating our gradient between our inputs with respect to our inputs for our predictions. That was poorly worded. We are calculating the gradient for the output with respect to the inputs. Is that good? Yeah. Okay, great. And we are specifying which specific class that we want to classify, that we want to actually make this input times gradient plot for. And that's what goes here. So if we want to do El Nino, that would be a 1, and La Nina, that would be a 0. We can go into more details about this function later, too, if you're interested. Okay, so this is just some fun pre-processing stuff that we have to do again because we didn't save the data. Why is it called tape? Why is it called tape?
A Turing machine here.
Yeah.
Yeah, maybe, yeah.
Some little back and forth.
It might be a callback to something like that because I know these Google folks do have a sense of humor.
Okay.
But that's actually a new update with TensorFlow 2, and it has broken a lot of the old code that folks have been using for the XAI methods. So this new tape functionality is sort of a thorn in my side right now. But
Anyway, it's magic and you just learn it.
yeah, exactly.
Correct.
Yeah.
Get to invent magic, get to name the magic
Exactly.
Yeah,
after their dog or whatever.
yeah. Yeah, they're dog tape.
It's the nice thing about not being software engineers. Yeah, okay, great. Okay, so now we're going to load in our trained neural network. And then we're just going to plot those composites again to make sure we have the same network loaded. Not necessary, but a nice check. These are just prettier plots of the plots we showed before, but they're the same data. Okay. So here is actually where we're doing our input times gradient calculation. And what I'm doing at the top here is just splitting our data into the correct predictions. They were all correct, so unnecessary for this problem, but it's there if you need it. And then I'm identifying where the neural network made a La Nina versus an El Nino prediction, and then I'm subsetting those inputs into La Nina and El Nino, just two different variables. These are just empty arrays that we're going to populate. And here's the fun part, where we actually call get gradients. So you're going to provide it with a sample in this for loop. This is for all the La Nina samples. In this bottom for loop, it's for the El Nino samples. We're going to calculate the gradients for each sample. I have a 0 here because we want to use the La Nina predictions. And that gives us a gradient map. And then what we're going to do is we're going to multiply these gradients by the original sample, and that's our input times gradient calculation. Cool. So we do that. That was super fast, am I right? Okay, great. We're going to reshape it because we flattened the images or the input SSTs for our artificial neural network, like Will mentioned. I'm just going to smooth them because they're a little bit messy. This just makes them a little prettier. And we know that as climate scientists that our SST fields are spatially correlated. So that's all right. And then how are we doing? Are we all caught up to, what is this? Not named cell. Okay, so here's the composite of the La Nina predictions. We've been looking at this before. So that's our input. And here's a composite of all of the gradients for those correct predictions. And you see, I'm going to zoom out for a second so we can see both color bars here. So we have negative SST anomalies in our expected region, and then we can see that the gradient is negative and largest over this El Nino region, or ENSA region. And what this means is that as SST in this region becomes more and more negative, our value at our output is becoming, for the La Nina prediction in particular, is becoming much larger. So that's why we have that negative value here. We can do the same for El Nino predictions. Now, as in this region, in this specific region, When the SSTs become more and more positive, we have a greater value in the El Nino output prediction. And that's why our gradient is positive. And then we can actually plot that input times gradient. And this is our final XAI heat map of the regions that were important for the predictions of La Nina and El Nino.
Okay. So let's move on to the second method, the backwards optimization. So with that, you'll just go over to this next notebook. And you're going to see a lot of things that are the same, so we'll load those libraries. And here's just a simple, yeah, let's just import sys. Oh, yeah, it's got to go up. There we go. There we are. So here's just another simple explanation of what we talked about in the presentation. So I'm not going to go through this, but for your reference, if you ever want to pull this notebook, you should be able to just look at this figure and it will explain sort of what's going on. One thing I didn't mention is that this backwards optimization is not, you're not constrained to only do it on the input layer. You could do it at any point in the network if you want to see, okay, what's my first layer of optimal inputs looking like? It would be obviously abstracted a little bit, especially if you're using something like a convolutional network, but there is some insight that you could pull from that. Say, okay, it's really looking at the gradient of these features. It would show a big gradient or like Laplacian, depending on what the figure actually pulls back. So I've seen some really cool work where rather than just focusing on the input, they focus on some of the inner workings of the network itself. So with that, I want to just have you quickly look at the gradient descent for backwards optimization function here. And there's a lot of hand-holding right at the top of just telling the network what it's supposed to do in certain cases. But let's start with this backwards optimization for class function. And essentially, I want you to focus on this little block of code here. So what this is saying is, okay, come in here, give me my target class. My target class is now the output. Oh, sorry, let's say that it is more than one neuron of our target class. For now, we have 2 neurons. So it hits this else statement, and it says, okay, what is the target class, either El Nino or La Nina? If I wanted to optimize that, I want it to be as close to 1 as possible. So I want this whole value to be 0. So I take this, I subtract it by 1, I square it, I take the mean, and now we have this sort of root mean squared error way of saying push the network from whatever state it is now to 1. So make this a positively optimally predicted class. We then feed this to the other function that we have above, this gradient descent for backwards optimization. We feed the model, we feed this loss tensor, and importantly, we feed the input matrix. So we're feeding this matrix of zeros or random noise, if you want to do that, to the matrix. It then says, push this random 0 towards this 1. We go up to this input. And again, this is a lot of hand-holding, but we are telling the algorithm exactly what piece we want to grab up here. But really, what we're trying to do is find the gradients within the network. So this is the list of gradients. And for this, we are calling this TensorFlow 1 version, grabbing these gradients. And then what we do is we iterate through however many epochs that we set it to iterate through. And it goes back and it adds this gradient times whatever learning rate you set to those inputs and reconstructs that forward image. So that was a lot of language, but if you go through that piece by piece, it should be super logical if you look at the schematic that we looked at before and then what the actual algorithm is doing. All it's saying is push this towards 1. I have an input space. Let's calculate the gradient and slowly add that gradient back to the 0 space. So you can think of it sort of as a tendency that we're adding. And then we'll eventually optimize until it says, okay, after this number of these inputs, epochs we've optimized. So I'm going to run that, grab the file again, prep the data, which is all things we've seen. and then load the neural network. If after this session you want to just play with your own neural network or mess with some of the parameters, I've also just ported over that code. So you can say, what if I had 4 hidden layers and it's this? And you can watch it train in different ways. But for now, we'll stick with our original network. Again, we'll evaluate the model, and we show the same composites. And then this is the part where we actually call the backwards optimization. So we're going to do this for 4,000 iterations. We're going to set the learning rate to 0.001. And we want to optimize for El Nino and La Nina. So these 2 different target class. So you can see we've named these El Nino and La Nina optimized backwards predictions. If you run this, it should show you the loss. And you'll notice this number is getting smaller and smaller until it's almost nothing. We then reshape these back to be in SST form. And we check, is this an optimal prediction? So what we did then is we just handed the prediction that it constructed back to the network. And it said, what are the odds that this is an El Nino? Well, it's 99.9% sure that this is an El Nino. What are the odds that this is a La Nina? It's 99.9% sure it's a La Nina. Let's see what those actually look like. Whoa. Whoa, well, they're out of the extended range. Sorry. There we go. And then you can see it has constructed what it thinks the optimal El Nino and La Nina is, and we see those big old blobs right in between the 2 features. And I'm just going to change our color map really quick so that we can take a better look at it. And you can see it's really optimized around this Nino 3.4 region in which we have defined the El Nino space. So this is what it thinks is the ideal La Nina or El Nino. Cool. And since you all, it doesn't sound like you think this is magic, like I thought it was, I'll just want to emphasize one more time, we handed this zeros and it reconstructed the state for us. It feels amazing to me. Okay, anyway.
There we go.
Thank you.
Wow, it's crazy.
Wonderful. So with that, we want to open it up for questions. And also, if you want to talk to us directly about the problems that you're thinking applying these sort of methods to, we'd be happy to chat about it. Cool.
Looks like we have 15 minutes-ish.
Is there one line up front where you could make this a 6-month prediction instead of a nowcast labeling?
You'd have to add lead.
Yeah, just
Yeah.
Exactly. Just shift
Yeah.
the array.
Yeah, then you could
just shift the array.
Yeah, you could just lag it, and then you could see what's the optimal. Yeah, so then you could look at
Roll
things.
the array if
Yeah,
you want.
exactly.
Yeah, so what that would construct is then these are the optimal SSTs prior to it. So you would hopefully see it, either NPM. Yeah, that'd be cool. That's actually, that's neat. We should have done that. I mean,
Could have wrote a paper.
yeah, I saw a talk this morning about someone constructing causal networks to do that exact thing using some fluctuation dissipation theory, but also pulling in neural networks. Yeah, so there's definitely folks that are starting to think in that direction. And I think, again, the thing that we probably want to highlight is that when you are starting these problems, make sure that the XAI is sort of the goal, rather than, we have this network that performs really well. The reviewers want to see some XAI in there. Because I often see that kind of happen, and the XAI is much weaker for it, and the scientific findings are weaker for it. So if you start your studies with the intention of we're going to be using these methods, that's where I see the biggest successes.
I do think we could code that up in like 15 minutes, though.
Yeah, we could
Yeah,
do it.
yeah, easily.
It's kind of neat. Yeah, we should try
I mean,
it.
yeah. I'm not doing anything after this.
Yeah, right?
I just want to ask, when your network has something like recurrence in it or like attention mechanisms, how well do these particular methods adapt to that?
I don't think they do.
Okay.
Do they?
The backwards optimization,
Oh, does it?
there should be no reason
Okay.
that it doesn't. The input times gradient doesn't seem like it should be a problem either. The issue is the more complex it
is,
gets,
yeah.
it really, you start to get that vanishing gradient, and it takes all kinds of weird pathways. So the ideal studies are very simple networks. And I've seen a lot of powerful stuff out of very, very simple networks with these methods. But
Yeah.
yeah, the tendency rate. Go ahead.
Sorry, I wouldn't use input times greater for that. Yeah. No, I don't know about backwards optimization.
I mean, it would probably be tough. But
Yeah,
yeah,
doable.
I thought I
Is
saw
that non-uniqueness? You ask it, show me a dog, it shows you a dog. Ask it again, we'll show you a different dog? Or is this all, all that information's actually in the weights? But it feels like the input is bigger than the weight set. So
Yeah.
how does it make details?
Well, if we gave it zeros, and if we give it zeros again, it's going to give us, and we've specified a network seed, it'll give you the same output.
There's a random number generator. in there,
Exactly.
Fluffing out the details.
Yeah, exactly.
Yeah.
Dithering or whatever they call it.
Yeah.
Yeah.
But if you give it different inputs, you could get like a space of different
Yeah.
optimal inputs. Yeah.
So a cool thing that DJ has done is he says, here's a storm pattern. How can I make this? How can I put a tornado into this prediction? And what he does is he hands it the actual, like an actual real life field, and he shows the shear start to be optimized for this kind of stuff. Very, very cool work. Yeah, but he walked out of the room. So yeah, you can also feed it. You don't have to feed it zeros. You can feed it an image and say, how would you change this image in order to make it an optimal?
You put in a skillful first guess, you'll get an even better
You get
optimum.
even better.
An
Yeah.
optimum or something.
Yeah.
Yeah, so you can seed it in that way.
Yeah.
Um,
I don't know how useful that would be for this, given it's 100% accurate.
yeah.
Yeah.
Well, that's where the 6
Where the 6 months forecast
Yeah,
would be
that might
awesome.
actually
Yeah.
do.
Yeah.
Yeah.
That is cool. Did I see questions? I'll be watching the chat for questions. No.
No.
Wonderful.
No question.
Are there things that folks have seen in the literature that they are curious about in like the XAI space? Not to put you on the spot.
Or you're wondering how you can apply it to your own research? Or you're just having a really good time? Yeah, okay.
There are some nice toolboxes now that have all these methods implemented into them. Captum is one really nice one. And
Investigate.
Investigate is one that runs off the TensorFlow libraries. For folks that are really into PyTorch, and I've moved all my stuff over to PyTorch, you have to do a little bit more of the legwork yourself. But I think that also ensures that you understand exactly what's going on with the method, so it's not always a bad thing. Yeah, let me find them. It's 2 N's in investigate, right?
Open neural network.
Yeah. Oh, that's why they do that.
Uh-huh.
That's fun.
And also, if you provide us with any follow-up materials or links you want to give people after the session, we'll make sure they get it.
Okay, great.
So Captum has a very nice, actually look, they've done a PyTorch implementation built on PyTorch. Okay,
That's great.
so you can do a lot of this stuff, but, and tutorials and references here. What I would caution against is thinking that the XAI part will be fast also. I think once you run the XAI method, that's where you really start to put your scientist hat on and say, okay, I've done this on this region or this many samples. How do I pick apart those samples such that they tell a coherent story that makes sense with my scientific background?
So the input is just the index or the temperature for 3.4? Because it looks like it's 324 by 5,000 or so.
It's tropical SSTs, the map, is their input into our network.
So it's every lat long location in the whole tropical band. And it's flattened out. So the 324 is the time index, and the other is the lat times long.
So hypothetically, if I were to assign a master's student of mine to transform this work into something that has a network that has two-dimensional input instead of one-dimensional input. Is that going to be very difficult to modify your, say, like BWO for class functions and that sort of thing?
No, it shouldn't be hard to do. The one thing you do is just flatten the input, right? If you didn't do a neural network or a feed-forward neural network, just reshape the input so that it's just like we do with EOFs, et cetera. Flatten it by shape by time, and then feed forward to the neural network. Now, that's what we did here, so that's the easiest way to do it. If you want to do two inputs, you can. These methods work really well for convolutional neural networks, or some way that you're accounting for that spatial extent. But yeah, both of these methods will apply well to sort of these 2D spaces.
Yep.
Yeah. So sounds like a fun project for a
Yeah.
master's student.
Hypothetically.
Hypothetically. Okay, so as we come up to 15 past the hour, we'll be headed to a 15-minute break.
I was gonna wait on our session to wrap up in here before announcement. We just have another minute or two if there's anyone.
Cool. Yeah, if there are any last questions. Also, we will provide our email addresses to the workshop, and they'll send them out if you ever have any questions about this stuff. I know, I guess I'm speaking for both of us. I'm very happy to help.
I'm also happy to.
Kirsten. Kidding. Yeah. So.
Okay, great.
Well, that brings us right up to 15 after. Let's take a moment to thank our workshop leaders.